different part of potential. That one possibility. Other possibility is that it's not due to DD fusion. Maybe it could be something else. That is, we may be barking at the wrong tree. Okay. Ashes. If Q value happens to be very small, then you can avoid lots of this radiation ashes, but it doesn't take 100% off. For that, you may need coherent mechanism, whatever. And that may be completely decoupled with this idea. It could be different mechanisms, which may be operating simultaneously, producing different things. Anyway, heat after death, according to this scheme, would involve short-lived final nuclear product. If you can produce short-lived final product, of course, it will have a heat after death. Now I come to 3D fusion. For 3D fusion, you have to solve a three-body Schrödinger equation, scattering problem. And one way to solve is go to so-called hyperspherical harmonic function expansion. And if you take lowest term or leading term in this expansion, then you get this formula. And that reduces a two-body equation. When you make this approximation, it's known as true three-body state in the West. In former Soviet Union, it's known as the democratic state because they were in a communist country. But anyway, one can write this equation from a three-body equation. And we thought we cannot solve this analytically, but luckily, this particular fraction allowed me to write the solution in terms of hypergeometrical function. So one can get the analytical solution, and once you get the analytical solution, then you can do the same thing, use optical theorem to introduce cross-section, and you get this familiar enhancement factor again. But the gamma factor will be, of course, different from two-body case, a little bit different, but nevertheless, one should make a comparison between those two. Now, what is the implication of that solution? For the democratic state or true state, solution from our solution, asymptotical behavior of the solution goes like this. Rho to the 5 second. Whereas conventional scattering solution goes like 1 over r. That's why scattering amplitude has length and cross-section will be square, so it's the area. For true three-body scattering state, the amplitude goes like length 5/2, square goes like L5. And if you want to calculate the rate, then of course three-body collision involves NQ rather than N square, and this cross-section we computed over there. But if you use a conventional two-body multiple collision, then you end up with a 5/5. And that essentially is the argument why when people say three-body fusion is occurring, my colleague will say you are crazy because of this argument. But if you go to new true three-body state solution, then formula becomes like that. And if the cross-section is comparable, then you gain by this density factor. Now, when we got this formula, we were surprised, but it comes out. So it will have enormous implication if Kasagi's observation is indeed correct. Because we need to ask him, other people to repeat the experiment, and even do the coincident experiment between proton helium-4 to see whether it's a really three-body process. So how many minutes do I have? Oh, I'm too early. You can ask a question. The conclusion. The new formulation based upon the optical theorem is less model independent than earlier one. And you can find the analytical solution if you make a reasonable assumption as to imaginary part of interaction. And if interaction range happens to be large, which I cannot prove at the moment mathematically, although for other cases people prove it, then near cancellation of gamma factor can occur. And furthermore, larger G fusion has larger fusion rate, which is a big surprise to me. And three-body scattering state. This is something one should really pursue. We haven't done the detailed numerical calculation, but we have order of magnitude estimate. And finally, caution. I'm a theoretician. Unless I can prove it mathematically, theoretically, it's still speculation. And I'm speculating here. But experiment will tell whether this is correct or not. Thank you.
We have time for a couple of questions.
One question. I've seen that the composition of your enhancement factor depends basically on the fact that you assume to be able to make use of an expansion in high angular momentum value, even for interactions at very low.
No, this is a low. I didn't take high partial wave. This is a S-wave case.
I see your abstract here.
No, not that. I told you don't read that abstract. First one. Abstract. First abstract you're reading is S-wave. Okay. It's S-wave derivation. This is S-wave derivation. The first abstract we are reading, this one, I guess. This one contains that, okay? Not higher partial wave.
Yes, a really point of interest. In my poster model outside, the basic interaction is a DDD interaction. So I find your presentation very interesting.
Yeah, if this is right, all of the speculation about transmutation has a theoretical justification.
That's right.
Okay. Now, this is speculation. Okay. I have not proven whether, from a theory, one can get the long-range potential for the imaginary part. Although we are working on it, I want to have a proof, mathematical proof.
This is very good. The other thing is that in this file, you would also have smaller contributions from D plus D plus D, 4Ds, 5Ds, 6Ds, 7Ds, and so on. So
Yeah, we are developing general formula for n-body system, but I don't know how it's going to turn out.
very nice talk.
Thank you.
Before I introduce the next speakers, let me remind you that tomorrow morning at 8:30, we will have the discussion. The poster viewing, and depending upon how Peter Hagelstein has decided to use the time, there will be answers to questions that I expect one should be here at 8:30 to get started.
I mean, it may be better. People might prefer to cut the poster view and have more discussion.
That's Peter's decision, I believe, correct, Peter? Peter will have a comment.
You can decide.
That will be done by the time you arrive in the morning. Let me introduce, I see Scar's here, and I see Dr. Chubb is here. Today we'll be speaking about ion band state theory. Let me put this on the top.
Okay, I think I'll just use this pointer here. Just a minute. Who wants to know? So Mr. Weddle dropped us. Okay, hold on. Scott and I are going to split our time. I'm going to talk about the Coulomb barrier problem, and he's going to talk about reaction physics. I want to show 5 points in my portion of the talk. First, I want to show you that ion band state physics is mainstream physics. I want to show you that electrochemically it's possible to occupy band states with the kind of long electrolysis that Fleischmann and Pons use. I want to show that being in a band state makes a fundamental difference in how an ion behaves. I want to show you how the Coulomb barrier is expressed in confined particle systems. And then I want to show you how in a large crystal the Coulomb barrier decreases with the size of the crystal. So this view graph shows 4 publications in mainstream physics, 2 from physical review letters concerned with band states. All of these are concerned with ion band states. 1 from Physical Review B and 1 from Nature. And a quote from the paper from Nature, which says, regarding ion band states, what is good enough for electrons is good enough for protons, their chemical counterparts, 2,000 times more massive. Now I want to look at the experimental situation in palladium deuteride with a simplified picture of the lattice, where we've replaced the lattice with a set of stacked cubes for this discussion. And we've taken a line through the centers of the cubes, up a column of the cubes. And what we plotted in this solid line up here is how the energy of the system varies as we move a deuterium atom from a long line AA. And what we see is a set of peaks and valleys where we have stable locations, we are assuming, in the center of these cubes, and saddle points at the interfaces between the cubes. And we show the normal situation here under chemical equilibrium conditions with about 60% or 70% of the valleys occupied. And this is at a chemical potential that corresponds to deuterium gas in contact with the surface of the palladium at room temperature. This does not generally give you fusion, or it doesn't give you fusion in this picture. Now, what the electrochemists do is they electroplate for a long time, in our view, and build up a surface barrier, a polarized surface barrier, which permits them to plate more ions to a higher concentration on the metal surface, and they raise the chemical potential of the system so that they have a higher average energy and a higher concentration of deuterium within the metal, or within the whole electrode. So that the equilibrium condition now becomes something like 9 valleys out of 10 being occupied by these deuterons. But at this higher average energy, one can get a small population of 10 to the minus 6 to 10 to the minus 4th, we believe, of states that populated that are close to the energy of the saddle points, such that the ions then tunnel very rapidly through these barriers, and they see the crystal as a whole rather than just the localized potential well. So these are the ion band state, band state ions, and to our view, they are the only species within this system that has anything to do with radiationless fusion. Now, why does this make any difference? We go back to an article published in Science in 1972 by Philip Anderson, and he points out that the various distinct fields in science that we're used to thinking of are separated by the breaking of various symmetries. And in particular, solid-state band-state physics, many body physics, is distinguished from chemistry, or chemistry in a solid in this case, by the breaking, or in this case, the non-breaking of lattice symmetry, whereas going to the chemical configurations, one breaks this lattice symmetry. So in Preparato's language, we're in the coherent situation here where things are tied to this repetitive lattice symmetry of the lattice. Now we will see that that makes a difference shortly. The next point I want to discuss is how one needs to view the Coulomb barrier in a confined system. And we're going to talk about two particle systems, two band-state deuterons in a lattice, where the boundary condition is the crystal as a whole rather than a local one, local potential well, and we're going to look at the helium atom. In the band-state system, two deuterons in a band state with no electron screening assumed, we have this normal form of the Schrödinger equation with the normal unscreened Coulomb repulsion potential. And this solution, this equation is written in terms of 6 variables, x1, y1, z1, x2, y2, z2. And if we want to really examine the Coulomb barrier problem, we need to convert to RCM, R12 coordinate systems, and then write our wave function in terms of the product of a function of RCM, which defines an amplitude at every point in the crystal, times a function which is only a function of the separation of the two particles, which I call a dimming function, g of R12. Okay, if this dimming function goes to 0 when R12 equals 0, then there is no wave function overlap. And that is the proper way to describe the barrier, affect the barrier on the system in this confined system or negative energy system, the bound system. And let's look at that in the case of the helium atom, which is a very well-known system. And what we see here is basically this GR12 system, which takes on values between 0 and 1. And in this case, we are looking at solutions on a sphere, and when we have the two electrons, in this case, on opposite sides of the atom, of the nucleus, we have a value of 1, and this shows how the wave function, the two electron wave function, dims as you bring the particles together. This is when they're close to the nucleus, this is when they're far away. Now you will note in this particular case that the electrons, this function does not go down to 0. And what that means is there is substantial overlap of these two electrons at R12 equals 0. And so if these electrons had the nuclear properties of deuterons, they would fuse. Now let's go to the question of Coulomb overlap with these very much heavier particles in the band state. Now we go back to the important difference in behavior of the many body particles as compared to the chemical particles. The basic thing is this unbroken symmetry requires that the amplitude distribution of the wave function be the same in each unit cell. And the mathematical functions that describe that are block functions. And we're interested in the eigenstates of the system, which are stationary, they're independent of time. And they describe the particles basically as fractionated into each unit cell. But many people do not like to think of the particles in this way, and you can expand these block functions into Wannier states, which give you a chemical picture where you have whole ions you get basically a sequence of snapshots of the system where whole ions are distributed at random in the various unit cells of the crystal. The stationary state then is an average over all of these chemical states. Now that's one important fact. The other important fact is that when it's dealing with a metal or metal deuteride, electron screenings is present. It plays the role, as Preparatus says, wherever the ion goes, the electrons are there because they have a great deal more mobility, and this is a very fast fluid, as he likes to think of it. But the big effect of this that's important to us is that the ions are in separate unit cells. These electrons screen their charge. Their electric fields do not extend from one ion to the other, so there's no interaction potential between these ions when they're in separate unit cells. And to illustrate this, we can look at the crystal with the two ions in it. We can look at all the unit cells of the crystal. And sometimes these ions end up both in the same unit cell. All the other unit cells are empty because we're talking about only two ions. And in this case, the Coulomb interaction potential is this normal value, E squared over R12. But the rest of the time, they're in separate unit cells, and then their Coulomb interaction is 0. And as I say, the eigenstate system is the average over all these snapshots of these virtual states. So if we return now to the eigenstate of the system, the time-independent stationary state, which is the block function, really corresponds to a description in which the particles are in every unit cell. The wave equation that gives you this picture, the proper interaction potential, is this average over the snapshots. And again, we can express the wave function as a product of this spatial part and the Deming function. But in this case, the Deming function provides a cusp. That interaction in the helium, the decrease, is a cusp with a point at the singularity point and the E squared over R12. That cusp is now present in every unit cell, and it, as Preparatus says, it's coherent. It's the same spot in every unit cell. And the problem of the Coulomb barrier then determines what is the amplitude of that cusp that minimizes the system energy. And we've done this variational analysis for large N cell, and we find a value that is of this form, and it has this factor 1 over N cell. So if N cell is large, not that large, this amplitude, the depth of the cusp becomes small, and by the time you even get to 10 nanometers in crystal size, you have complete overlap.
Sorry, let me just have these. That's okay. Thanks, Uncle Talbot. You gave me 8 minutes. One thing that Talbot did not emphasize when he was starting.
Just leave it down there.
That was a very important point.
Okay.
A very important point that distinguishes everything we say from everything that Dr. Kim says and Dr. Preparata says is that the energy in the problem is negative. Now, that's a counterintuitive notion. The energy in the problem is negative. The boundary conditions of the problem change. Talbot did not emphasize the business about cusps, which is a very important point. When you have cusps, you have discontinuities in momentum. This is mainstream atomic physics, and it's not part of conventional Gamow theory. When you have cusps, Gamow theory is invalid, and that is the basis of minimizing the energy that leads to the results. So Talbot left me in a lurch, but that's okay. We're an uncle-nephew team. Now, the point is that there are different boundary conditions associated with band theory, and they are distinctly different from what Giuliano Preparata said in one very important way. The notion of cusps, discontinuities, and momentum affects kinetic energy. Giuliano Preparata does not treat kinetic energy the way modern band theory does treat it, but he does a very good job of observing that it is necessary in solids to think about minimizing the energy and minimization principles. And in the parlance of modern band state theory, What is involved is a self-consistent quantum field theory that yields something called band transport theory as a semi-classical limit. In the process, by being self-consistent, and Giuliano says you can't solve these things, you can solve them self-consistently. And that's an important rule about band theory. It says a lot about solids. It's been developed very well. It converts a highly nonlinear problem into a linear problem, and then takes and has a microscopic theory based on local density theory that does this. The band theory requires periodic symmetry. That's another very important point, which introduces the mathematics of discontinuous functions, including cusps, including the kinds of things that completely invalidate Gamow theory. The momentum variable k is defined only at discrete values, and it is reminiscent of a momentum, but it's not a momentum, and I will get back to that point. Key to this is how the whole thing started. 60 years ago, band theory actually began in 1929 when Felix Bloch made an interesting observation. He said that one can start thinking about what would normally be like a distribution function, a Boltzmann distribution function, and require that you have a notion of periodic order which would remove dependence of the Boltzmann distribution function on position. And in the process, you introduce this notion that things aren't where you think they are. They're wave-like. Now, this is not crazy. This is the way electrons actually work in solids. And what happens is people have developed well-defined microscopic theories based on quantum field theory that give you back as a semi-classical limit this result. These quantities in here are group velocities. They're like momenta over positions. So this is like a density times a velocity, and that's how you get charge transport. And this solves another mystery. You can have a reaction that's distributed. The G's, which are the fundamental quantum field theoretic objects, are the things that dictate reactions, but they're distributed everywhere. And there's nothing about saying that you're taking a charge and banging it all up. All it is a statement that you really don't know where things are, and you take a semi-classical limit of something that is microscopic, and you come up with an answer. And, you know, it's a reduction to numbers. I mean, you can view solid-state physics as a reduction to numbers. It works quite well. Now, this has some details of what goes in. There's a process of solving single particle equations, and you ignore correlation initially, and the calculations show that actually, well, you self-consistency, you actually can solve for potentials with today's computers quite accurately. You can solve for self-consistent potentials that treat as a starting point all the other charges around. No shape approximations, everything, the whole shebang. And you start with this, and you actually include all the electrons. So there are a lot of details. The key point is you do a good job of the kinetic energy, not done by Giuliano Preparata. The details are there.
By the way.
What?
You're wrong, by the way.
Well, anyhow, let me go. You ignore the exchange operation initially, and you treat things in this framework, writing things in this manner. This gives you a problem of solving single particle states. The important point, though, that distinguishes this also is that you always assume that you have a periodic potential and you solve for these eigenvalues. And the solutions are called block functions, and you bring back exchange. You treat the Coulomb barrier between particle-particle as a perturbation. And the theory only works when it's a small perturbation, and that actually imposes constraints on the theory. It does turn out that one can show by the more sophisticated treatment that Talbot talked about for the two-particle case that as a function of crystal size, the effects of particle-particle correlation can become small. Basic point is implications for potential nuclear reactions under the rules of solid-state physics. Cold fusion can occur as a transformation of wave-like deuterium into wave-like helium-4. The energy release from the transformation involves no high energy concentration and no high energy particles are emitted. This is all because you're working with the G's. 4 minutes? Okay. There are a number of things associated with the occupation of ion band states I won't go into. We've discussed this at length in the literature. Once the states become occupied and you minimize, they will become occupied if energy minimization allows it. And there's an important point about electronic structure that's very well known associated with palladium deuteride as exemplified by the things that Talbot showed, that it will form under certain conditions. An important point, though, is that we've extended things. We've talked about analogous theories to the local density theory for electrons, and there are things associated with fractional concentrations. Point is, you can arrive at a self-consistent set of results when concentrations, these are the active components, are sufficiently small. There's, you know, a mathematics associated, which I won't really bore you with. There are important implications associated with how nuclear reactions can occur. The band states, to occupy a band state, there are constraints, and it imposes important rules associated with the possibility of where nucleons can overlap and how they can interact with each other. It's necessary to have things sufficiently diffuse. Proton-neutron pairs cannot be broken, and that actually follows in order to require that you can have a meaningful band function representation. It's associated with the quantum field theory converging to a meaningful result. Important point concerns this business about collisions, momentum not being conserved, this whole business about discontinuities. There's an important point about energies. This is especially important, we believe, in cold fusion. It's associated with the fact that the eigenvalues that are block functions are periodic functions of these magical things called reciprocal lattice vectors that don't change the periodic order of the lattice. These are called Umlauf processes. They've been known since the 30s. Rudolf Peierls did it. There's a formalism that's associated with this, with putting in reactions and so forth and so on. The big message I want to get across is that this diffuse thing is very different. There are ion band states are radiationless for a number of reasons that I won't go into. I want to summarize the theory predictions that came out as a result of this. Prior to measurement, we predicted that helium-4 would be the reaction product, that there's a need for periodic order, that reaction rate is proportional to the square of band state D plus concentration. We need values of x near and 1 in ordered domains. Then there's a requirement for electrolysis of an overpotential. The reaction should be radiationless, all made prior to observation. Low energy helium-4 to be found primarily in regions outside heat-producing crystal, that is, cracks, interfaces, and outside the electrodes prior to Melvin Miles's measurements. The reaction rate should, this is an interesting one, should be proportional to final state concentration of helium-4 in the ion band state, which is a kind of self-perpetuating feedback type thing. Interesting implications. And also that there is production of byproduct tritium is likely to be enhanced by hydrogen-1 impurities. The hydrogens as well as the tritiums can also occupy ion band states. Finally, there are higher power densities from small crystals, but crystals must be larger than roughly 0.4 microns. Good crystals are necessary. For N-cell, for the number of unit cells equal to 10 to the 9th and D plus concentrations equal roughly 10 to the minus 6, you get a power amount of that. We've gone in, we've gotten into design specifications. There are a number of important parameters that come out of this. All right.
Thank you I'm going to do the only one again.
It's okay.
Okay, I want to ask you quickly, what do you mean by negative energy other than just two D's going together? Sure, they're negative energy too compared to what they are separated.
What I mean by negative energy.
se gli elettroni c'è un vantaggio in cioè se gli elettroni non ci preferenzialmente in questa direzione, allora l'effetto viene innanzi. Viene innanzi perché allora tu puoi vedere che questa è in questa direzione qua dove va a sedere il deuterio e poi quello che arriva in eccesso lo vede solamente. E la cosa importante del plasma, la gente non ha capito, che questa cosa dinamica dà un'inerzia al plasma, per cui è come se avesse una massa più grande.
I guess the cello. Excited bands of the excited space, which is the other thing.
No, I mean, standing on this side. Okay.
Some time ago, Gene Mallove twisted my arm to write an article for his magazine. I called it A Plethora of Miracles, and I described 3 miracles. The title of this talk, the 3 miracles I'm talking about are the 3 miracles from the paper. But I've noticed that John Huizenga has 3 miracles. I'm completely sure they have nothing to do with my 3 miracles. Basically, the introduction will summarize the approach and what's new, what's old. I'll be talking about anomalous energy transfer. In order to get anomalous energy transfer, I'm going to need phonon lasers. I'll talk a little bit about phonon lasers and how desorption in highly loaded metal hydrides can produce surface phonon lasers. I've been working on neutron hopping, and then I will summarize. The basis for my arguments come from 2 considerations. As I see it, there's 2 outstanding problems the community faces. One is, if any of this is going to be real, there has to be a way to transfer energy to or from the lattice. And not a little bit of energy, but a lot of energy, hundreds of kilovolts, megavolts, and so forth. The second issue is faced by the community, more or less has to do with the Coulomb barrier. If there's to be fusion reactions, a way has to be found to overcome the Coulomb barrier. More generally, if there's going to be reactions of any sort, reactions between nuclei ultimately involve having strong force interactions, which are short range between nuclei. The nuclei tend to be charged, and they push one another against. So Coulomb repulsion is going to come into play. So Coulomb barrier has to be addressed independent of what kind of reaction that you're talking about, fusion or some other approach. My approach for energy transfer is frequency shifting of phonon modes. The basic idea is if you can shift the frequency of a phonon mode a little bit, then a phonon that's in that phonon mode will have its frequency shifted by a little bit. The energy transfer must be made up by that which causes the frequency shift. If you take that idea and put a lot of phonons in a phonon node, then when the phonon node shifts frequency, the energy transfer can be amplified by the number of phonon nodes. The business about neutron hopping, the way I think about it these days is we know that electrons hop in crystals. The mathematics that describe electron hopping crystals, one such model is the Anderson model. The fundamental Hamiltonian for the Anderson model turns out also to describe configuration mixing between neutrons, valence neutrons, and conduction neutrons in nuclei. And so in a lattice, the mixing, the strong force-induced mixing of the orbitals is going to induce coupling between valence and conduction neutron states. This leads to second-order neutron hopping effect, and I'll be discussing further how that works. Let me, in my introduction, summarize what the theory would do if it works and if it's right. If lattice energy transfer works, it will produce recoil electrons and ions that are fast. And in the case of ions, it can be 20 volts up to kilovolts. In the case of electrons, it can be kilovolts. In the case of deuterons or hydrogen, it can be megavolts. In the case of recoil off of palladium. If you produce fast ions, if they happen to be deuterons, and if they're going a few kilovolts, they can bang into each other and lead to DD fusion within the theory. I'll show the rate for that. Helium-4, if the lattice inputs energy into nuclei, in the limit that you've got about 5 megavolts of energy transfer, you can induce alpha decay from palladium. Additionally, beta decay can be induced. This alpha decay was supposed to be fission and host lattice activation. My spelling checker's not working so good. My view graphs. In the limit that neutron hopping works in the absence of any lattice energy transfer, you would expect a weak gamma emission. Namely, if neutrons actually participate in hopping, sometimes they'll hop into the presence of something that can capture the neutron. I'll be talking about this process. If you can drive the lattice with a phonon, since the neutrons are massive, there's a coupling between the phonon field and the neutron hopping effect. Predicted a phonon-driven lattice, the effect is much larger. In a driven lattice, then the prospects of seeing either band shift or gamma emission are much greater if the lattice is driven. Neutron hopping itself, the neutrons can originate only from nuclei with outer S neutrons, and there's a further requirement that you have to have 2 neighboring isotopes. For example, if you have silicon-29, silicon comes with silicon-28, 29, 30. If you have silicon-29, a neutron originates from silicon-29, it can land on the silicon-28s to form nearly resonant silicon-29s. So the number of elements that can participate in this kind of process in principle are limited to the 1s, 2s, and 3s outer neutron nuclei. So it's a rather small collection. From my point of view, in the cold fusion business, if deuterium accepts the neutron, it can make tritium, and I think that's important. Silicon can be both donor and acceptor, and I think that's important as well. If you put the neutron hopping together with the energy shift, then you have a chance of getting production. When I made up this view graph, I was very optimistic, and in the Pons-Fleischmann experiments I'm viewing now, silicon as being a prime candidate for participating in the neutron hopping, and hence being the fuel and the ash. In principle, if it works this way, you burn silicon-29 and you make silicon-30 and silicon-28. After musing further about it, listening to various talks, the donor has to come from the list from the other paper. The acceptor has to have an S state. And I've been musing during this conference as to whether there's relatively long-lived excited state nuclei with outer S neutron symmetry. If that's true, the list of participants can be a little bit larger. Tritium production is, as I've said, and within the theory, other reactions would be possible with this list of materials. Okay. In order to figure out what's new or what's old, my view of what's old here has to do with what was presented previously. The energy transfer mechanism was presented previously. The fact that I need a large number of phonons, we know. The fact that this mechanism, if it works, would produce these anomalies and heat production, tritium production, I've discussed before. I'll review them briefly. What is new? What's happened recently? I have a new mechanism to pump a phonon laser, which I'll discuss. The basic idea is that desorption, when it's exothermic, should provide phonon gain for surface phonon modes. And in the limit that you are exothermic and you're desorbing rapidly, I'm coming to the point of view that you couldn't help but have surface phonon gain. Some analysis of the laser's been done, the phonon laser, and the results were a little bit different than I was hoping for and than I expected. Basically, I thought I needed to make an optical phonon laser, and I went to the APS to present it, and I learned there that the phonon lifetimes for metal hydrides at room temperature are really quite short, in the neighborhood of a picosecond. That makes it real difficult to maintain coherence in order to do things like transferring energy or making phonon lasers and so forth. Consequently, the pump requirements to sustain a phonon laser in the presence of such a tremendously short lifetime is tough. So an optical phonon laser looks difficult. Acoustical phonon lasers look much more probable. And after thinking further, it dawned on me that there's a way to transfer energy even if you have an acoustical phonon laser by nonlinear coupling with the optical phonon modes. The other thing that's new, in this neutron hopping business, if you're going to prove that neutrons hop, you need a clear demonstration of it. And it occurred to me that if I had a clean example, I chose the example of crystalline silicon, which is very well known, and I attempted to make up a model for neutron hopping in crystalline silicon to see whether it would be observable. I think neutron hopping in silicon may actually be observable. Okay, I'll talk briefly about anomalous energy transfer. Thank you. The basic idea is that if you have a phonon band gap, if you have phonon modes and if you have a phonon band gap, in the limit that you change what the phonon modes are due to, you can induce phonon modes to go from one band to the other, hence they jump a band gap. There's many examples of this. The first I found was impurity modes of hydrogen deuterium in a metal hydride at low concentration. If you added a neutron to hydrogen, it would become deuterium. The phonon modes from the hydrogen would be here, phonon modes from deuterium would be here. If you added a neutron, the phonon modes have to move to be consistent. Last conference, it dawned on me that vacancy modes in a metal hydride would work the same way. I postulated that if you had the Fukai type of structure locally, if you have palladium vacancy, you have the deuterons remaining basically in their octahedral sites, but if the palladium's gone, the potential's a little bit softer, and the phonon mode frequencies would go down. If you have 8 deuterons, perhaps you have modes here. If you have 7 deuterons, the potential's even softer, and perhaps you could get another impurity band, vacancy band. So the basic idea is that if you have your phonon modes, and you can get them very highly excited, perhaps they'll jump. And if the first one jumps, then it cleans it out and leaves the second one showing. The second one jumps, cleans that out, and leaves the third one showing. And so, in principle, you could have a number of these phonon modes jump if you can get them highly excited. I calculated reaction rates for pretty much everything I could think of. They're in the Fusion Technology Transactions conference proceedings. For example, if you have deuterons that are accelerated as a function of energy transfer, you could calculate the rate of production of fast deuterons. Additionally, with electrons, in the case of electrons, the electron's pretty light, so you have to transfer a fair amount of energy for it to recoil fast enough to push something out of the place in order to change the number of vacancies. In this case, I'm pushing against a deuteron. And the limit that I push against a palladium nucleus, I have to have much more energy. The fast deuterons, in the limit that they have kilovolts worth of energy, which I guess is around here, which occurs with a finite but lower reaction rate, they'll make DD fusion neutrons. And I calculated the reaction rate for that last year. To summarize the essence of the computation, you get the calculated rate up to the point where you can initiate electron recoil, and then the process is shorted out. It won't occur further. The magnitude of the rate for the DD fusion neutron tends to agree with the low-level random emission rate folks observe. The bursts would be accounted for by ionizing neutrons directly off of deuterium, and that can occur if it happens at all at a very much higher rate. I'll talk now briefly about phonon lasers. As I mentioned, the motivation for phonon laser is that if I want to have large energy transfer, n times h bar delta meg, I need n large. A phonon laser can produce a very large number of phonons per node. People actually have demonstrated phonon lasers. Phonon lasers were of interest to the laser communities following the inception of the laser around 1960. Charlie Towns proposed phonon lasers. Work started immediately on them, and phonon lasers were demonstrated through all kinds of mechanisms. Phonon lasers have been demonstrated up to 0.87 terahertz. One scheme is to come in with a laser, pump a crystal, pump impurity atoms in a crystal. In this case, it pumps from this level up to this level. This guy can come down by phonon decay, and then you have a fast non-phononic decay to the ground state. This in lanthanum fluoride, erbium impurities have produced a laser at 0.2 terahertz. At Bell Labs in 1980, WHO managed to optically pump chromium in ruby and produced 100 gain lengths at 0.87 terahertz. I'm interested in a slightly different mechanism for pumping a phonon laser. Phonon lasers have been pumped by about 5 different mechanisms so far. I'm looking at desorption, what I'll call exothermic desorption. And my definition of desorption, I think of the desorption of the hydrogen going out. So if the hydrogen goes out such that inside's got more energy and outside's got less energy, then that's, I'll call that exothermic desorption. And I've noticed that all the electrochemists will call that endothermic. And so I don't know that I'm going to change for this talk, but to warn you that there's a sign reversal between language here. But if you had a bare metallic surface of a metal hydride, you could compute the potential, isopotential lines. In this case, it was done for hypothetical copper hydride. The basic idea is out here, away from the metal surface, the deuterons or hydrogen atoms go together and you have a molecule. But as you approach the surface, the potentials are such that the hydrogen would separate as it goes into the metal, and vice versa. If you think of it, you have a molecule coming in that spreads out, going into the lattice, what comes out, it's separated and then they come together to push out. There's a huge literature on this. If I were to simplify this dramatically from the point of view of a laser, I might look at the process like this. I might view near the surface the hydrogen or deuterons being at one energy relative to the molecular species in the limit that the desorption is exothermic. By my way of speaking, this energy level is above this energy level. In this case, the hydrogen is pushed away from the surface of the metal, so there's no hydrogen accumulation, molecular hydrogen accumulation on the surface. This is a classical analog of what in optical lasers is called an excimer laser. In excimer lasers, you've got a stable excited state, molecular excited state, for example, like KRF. The lower laser state after you made a rate of decay is unstable. It has a potential that looks something like this. The two atoms push each other apart. And it makes a very good laser with no lower laser state population. And this I'm viewing as being the analog. As we've heard a number of times, this is taking in the low loading regime under about 0.8, taking the experimental data for the delta enthalpy, which Steve Krashbaker will talk about. It's been talked about a number of times at conferences. If you extrapolate it up and use units of electron volts per molecule, then it goes something like this. Up in this region, the desorption is exothermic. If I focus in on the region where it's exothermic, it looks something like this. I don't actually know where the axis crosses. I use the value that Steve Krashbaker recommended for me for hydrogen. If I go to even higher loading, That's where the threshold is for optical phonon generation. Acoustical phonon laser generation would be somewhat lower. So the basic idea for a desorption-driven phonon laser, if I have a pictogram, it looks something like this. The molecular species comes out, and there'll be a surface phonon mode, which will be highly excited. You can calculate the threshold condition for such a laser. You can do the atomic physics and do the quantum mechanics and get a laser model, and you get all kinds of great expressions and so forth. But in the end, this kind of laser, at least as an optical phonon laser, is limited by the kinetics. The basic condition for gain is you have to make more phonons than you destroy. The number of phonons you destroy is the number of phonons you have present in a phonon mode volume divided by the lifetime. The number you create are the average number of phonons you make per molecular desorption times the desorption flux times the area of the phonon mode. The threshold for an optical phonon laser, which I've been hoping to do, you can evaluate, and essentially when all said and done, it's the surface density of hydrogen divided by the lifetime, which is this number, which is this absolutely enormous number, desorption flux. First question is such a desorption flux possible even theoretically? And you can calculate the desorption flux assuming you have highly loaded palladium and you remove the surface instantaneously. And it turns out at high loading, the thermodynamics suggests that in fact such large fluxes are at least theoretically possible. The downside is that the desorption time goes way down. And so if you actually could achieve such a large flux, you couldn't achieve it for very long. There's additionally the problem that if you had such a large desorption flux, how do you get the hydrogen or deuterium there to actually desorb at such a high rate? You can make a model up for diffusion and show diffusion can't do it even in principle by many orders of magnitude. If you look at the darkened term, the cone effect type terms, you can do better, but you still can't sustain such a large desorption flux. So consequently, I seem to be in the business of proving that my idea couldn't work, that it doesn't seem like I can make an optical phonon laser at the frequencies that I need to in order to make things work, at least not in a metal deuteride. If I have a low temperature alkali halide or deuteride, then I could use optical methods to make a phonon laser and perhaps demonstrate the basic effect. So after having gotten rather discouraged, I picked myself up and said, well, clearly this mechanism can make acoustical phonon lasers, and the more exothermic you are and the faster you can desorb, the more gain that you'll have at higher frequency for acoustical lasers. And metal hydrides are tremendously nonlinear in terms of their phonon dynamics. Fourth order coupling of phonon modes is a dominant effect in metal hydrides. And so you can imagine that the nonlinearities are going to couple acoustical modes to optical modes, such that if I have initial state and final state that are highly excited acoustical mode systems, that there's going to be an admixture of the optical mode. So if the optical mode jump the band gap, they have a finite possibility of taking along their acoustical mode phonons. And I think that this is perhaps a rather important notion because acoustical lasers clearly, the prospects for acoustical lasers in Pons-Fleischmann type systems is rather good. So basic idea, the old way is that energy transfer would happen by having phonon modes go up here and having the phonon laser work here. But now the idea is way down here or even lower to have the phonon laser work in acoustical modes. And when this mode jumps the band gap, that the acoustical modes go along with it due to the mixing. Okay. I want to talk now briefly about neutron hopping. The basic idea is The basic idea is you've got bound neutrons, and as an example, the outer 2s neutron of silicon-29 in a lattice to lowest order, they're degenerate. They're not actually degenerate. The dipole-dipole splitting gives you a line width of about 5 times 10 minus 13 electron volts, which you can calculate theoretically and which has been measured experimentally as well. You have continuum states, which are, in the case of silicon, up above the valence level by about 8.5 MeV. The mixing between the bound states and the free states, if it occurs, gives you a Hamiltonian, which is the neutron analog of the Anderson Hamiltonian. If there exists a coupling matrix element, then this model is appropriate. First question is, does there exist a strong force coupling matrix element? In the electronic problem, this kind of coupling matrix element would generally be assumed to be zero by Brillouin's theorem. Basic idea is that if you have a fixed core Hartree-Fock equation, if the lower core remains fixed and you have a one shell promotion, that you can show that for a Hartree-Fock solution that there's no matrix element whatsoever. So out of the box, the electron analog of this mechanism is very strongly damped, and the only way there can be a non-zero matrix element is due to correlation effects. It turns out silicon isotopes are quite well known. In nuclear structure, they're considered part of the 2s1d shell system that shows very strong correlation effects. One indication of this is the magnetic moment. If silicon-28, some people think of as being a closed shell nucleus with filled 1s, 1p 1/2, 1p 3/2, and 1d 5/2, both proton and neutron orbitals. The extra neutron goes into the 2s orbital. If it were pure 2s, then the magnetic moment of silicon-29 would be equal to the free neutron value, or one neutron value, which would be minus 1.91 nuclear magnetons. The experimental number is minus 0.56 nuclear magnetons, which comes about by correlation effects or core relaxation effects. There's been a theory developed for this, originally from the 1950s, early 1950s, and there's been very extensive analyses of this through the 70s, some papers even more recent. Basic idea is to use perturbation theory and to calculate the corrections in the nucleomagnetic moment by including excited state configurations. The same theory can be adopted to calculate the nuclear matrix element. The ratio of the coefficients that appear in here have amplitude in the neighborhood of about 0.2 to 0.3 in the nuclear magnetic moment calculations. I've set up I've used John Nagel's Hartree-Fock code for nuclear structure to get some nuclear orbitals, and I've set up some angular momentum. I've calculated about 500 intermediate states on a computer for this. The ones that I've done so far involve one nucleon, different configurations, and I get a value of about 40 kilovolts in terms of this reduced number for the matrix element, including those one nucleon terms. By comparing with the magnetic moment calculation, it's rather clear that the answer, including the larger, the ones that calculate differ by 2 nucleons, the ones that differ by 1 will be larger. And I think that the number is about 250 kilovolts, plus or minus about a factor of 2. So I can take that and I can put it into the model and set up a model to calculate neutron hopping. My idealized model is to take a crystal in silicon and look for neutron hopping. It turns out there's a rather big effect that comes out of silicon. Silicon has a diamond structure. There's 2 interpenetrating FCC lattices. Last year when I spoke, I was considering simple cubic lattice, and simple cubic lattice couldn't change the momentum of the virtual neutrons. But silicon with the internal structure can backscatter the neutrons, and so I'm getting a much larger effect. The same effect would happen with the sodium chloride structure lattice. So what I've done is I've kept the two FCC sublattices is number 1 and number 2, and the continuum is number 3. Anyway, I can use this model in these formulations, and I can calculate the free neutron distribution explicitly, and I can show the localized part, and I can show the delocalized part. So it's a rather clean way to look at neutron delocalization. Perturbation theory works rather well for this. I can calculate the effects due to having the delocalized neutrons hopping to other silicon, and it gives me an eigenvalue equation, which I can solve. And it turns out that, again, the advantage of this problem is you know everything, so you can get exact solutions. The relevant energy scale for the neutron hopping is determined by the atomic physics parameters, and for the thermal case, it's 1 electron volt. Showing up in the matrix element here is a Mossbauer pip, namely to get resonant scattering. When a neutron hops from one nucleus to another, there's a question of how much energy transfer occurs. Last year, I assumed the energy transfer was 0. It's dawned on me that this energy transfer is not going to be 0, in fact. And in fact, the theory for it is the same theory as is used for the calculation of the Mossbauer pip line shape. In the limit that you didn't have losses, you can calculate the Mossbauer line shape for the average energy exchange for a neutron hop. And it's in the neighborhood of a nano electron volt. It comes about by fluctuations in the occupation of phonon nodes. Unfortunately, in the presence of phonon collisions, the model that I've got here is naive and simplistic. As it turns out, I don't actually know what the energy transfer is on the Mossbauer part of the interaction, because as near as I can tell, nobody's ever done this kind of computation in the presence of collisions. If I were to use that value, I get a band shift, which is on the order of 5 times 10 to the minus 13. No, the natural is 5 times 10 to the minus 13th. The calculate is 6 times 10 to the minus 17th, which is too small to be observable. The gamma emission rate from the thermally induced effect, you can calculate it exactly, modulo the uncertainties in the Mossbauer energy exchange. And you get a number in the neighborhood of 5 times 10 to the minus 6 gammas per cubic centimeter per second for silicon that's very hot. The basic idea is that this number is sufficiently small that it's not easily observable. But on the other hand, it is in principle observable. For example, if you took about 50 pounds of silicon, heated it up at the bottom of Kamiokande, and if Kamiokande could actually measure 2.1 MeV gammas, this level would get you signals or counts once every 20 minutes or so. The calculation applies to an experiment, the schematic of which looks like this. You put your silicon into a furnace, you use a gamma counter to measure it. The conclusions for this neutron hopping section business is there is a neutron hopping effect. We've calculated it. The basic effect, the math shows it can be strongly enhanced in a driven phonon field. So the idea is you take a brick of silicon, you come in with a terahertz laser, drive it strongly. The gamma emission rate from the driven system should be larger by somewhere between 6 to 10 orders of magnitude. So I have high hopes for this being observable on the lab bench, if it's right. Let me finish up by discussing the prospects of excess heat production by the neutron hopping coupled with the energy transfer mechanism. What's new is that in lattices with complex unit cells, there's internal Bragg scattering, which according to theory makes all the difference in the world. Last year, I was worried as to whether S-wave or P-wave nuclei could participate, and it's completely clear now that the S-waves are the only ones that have a chance. The donor nuclei must be from this list. The acceptors, in the limit that there's excited state S-wave nuclei, or you could produce unstable final states, can come from a larger list. You can make up a model for the heat production. You have to have at least 2 degenerate levels for your donor states. For sodium chloride or diamond structure is fine. Have the continuum and we have the acceptors. We can include the Bragg scattering of the virtual neutrons in this form and extract the non-local part of it explicitly. And we can do that, and we can get the reaction rate estimate. Formally, it looks like this. I've been calculating the equivalent of this for the silicon in quite a bit of detail. I haven't done the equivalent for the heat generation constellation cells, largely because I really am not completely sure what the structure is of the outer layers where there's some silicon. My friends tell me that it's a really complicated mess with all kinds of stuff in it. But in the case of crystalline silicon, I can evaluate these things exactly. But if I try to go for an order of magnitude estimate, I get expressions that typically look like this. It's proportional to the interaction matrix element to the 8th, Mossbauer energy squared, ionization potential of neutron to the 4th, and density of states. If I plug all of that in, I get heat production rates under what I will honestly admit to be optimistic assumptions that might be in a general ballpark of what it is folks are claiming experimentally. The key uncertainty in this is the choice of the Mossbauer alignment. I need a better model for that. The other assumption is that I'm driving it phononically very strong, which makes the neutron hopping be less inhibited. If I summarize the presentation, I see the guillotine coming down on me. The conclusions are the following, that there's an energy transfer mechanism now that looks like a viable transfer mechanism. I have a photon laser mechanism now by exothermic desorption, and it has the nice feature that it doesn't kick in until the desorption is exothermic, which means in palladium deuteride you need high loading to make that work. And moreover, the faster the desorption, the stronger the laser effect, which is in agreement with that flux model Mike McCoubrey presented on Monday, which I thank him for. The optical version of the photon laser doesn't look like it's going to work. It's too hard, but the acoustical one does look like it's going to work. If it does work, you get your neutrons, gammas, lattice activation, alpha particles, and so forth. The neutron hopping mechanism itself, that looks like it's solid physics, it's demonstratable in independent of cold fusion. But if I include it with the frequency shift, then it could account for heat and tritium. Future work, well, there's lots and lots of future work. I need a better Mossbauer model. I need a better photon laser model. At the moment, I'm sure that there's photon lasers, but the question of what frequency photon lasers and the frequency that's available depends on what the exothermic desorption flux is. The larger the cupping, the higher frequency you can get to. I need to do further study of problems to demonstrate the individual mechanisms by themselves. And finally, one thing that I need to do, as well as what probably all the theorists in the business need to do, is we need to make a better connection with experiment. Specifically, what we need to do is to figure out what experiments could be done to test certain aspects of the theory independent of what's been done already. For example, I think that people can measure phonon surface lasers in experiments that they're doing now. And I think the silicon isotope ratio should be checked in the experiments, but I think the silicon gamma emission would be a very interesting experiment to do as a demonstration of basic physics. And the guillotine comes down.
Could we have just a couple of questions?
Did I understand you right when you said that silicon was the very best acceptor for neutron jumping?
I'm not saying it's the best. I'm saying that of the experiments that have been done, it seems to be the strongest candidate for being a participant.
something to do with its role as a semiconductor sleep?
No, it's purely comes about because the outer neutrons in the silicon isotopes are 2s neutrons, and it's also the fact that in cold fusion experiments, many of them have been done in borosilicate glass or with added silicon, so there's silicon in near the surface.
Okay. I'm very pleased with your taking up the neutron as one of the agents to work in cold fusion development. As you know, I have already proposed for 1.5 about the trapped neutron diffusion mechanism. And as you formulated in mathematical form, I proposed several mechanisms in which neutron was in the cold fusion. And one of the mechanisms is neutron mesmer effect, which is published in Illinois Watchment last year. And your mathematical formulation is enlarged and made complete calculation of one point of my model. So I'm very pleased with your treatment. But
glad that my model's doing something for somebody.
I proposed in the paper appeared in Illinois Watchment. Silicon is one of the candidates to give some effect in the cold fusion. And the point of view is somewhat different from yours, but the direction of the consideration is very similar. So I hope your treatment will become more complete and support my model.
I think the appropriate statement is that great minds grovel in similar gutters or something.
We have basically a couple of things that need to be done. Peter was going to review quickly in about the next 10 minutes the papers, the posters which were up, and then what we were going to do was spend a few minutes with the authors of the papers, if you will, participating in a data extraction exercise, which Peter has outlined, and Tom Passel has agreed to act as scribe for that. The sort of faster we get through that, then we'll get to a discussion in which I'd like to invite comments and discussions in general across the theory papers that you've heard and read about. So that's a nice way of saying, Peter, that's the end of your questions section. And I'd like to thank you again. Now I want
off the hook.
Well, you're off the hook at this moment. What we'd like to do at this point, though, is if you could do your quick run through of the posters, and then we'll get on to the data extraction.
Okay. Before the conference, I heard from Martin Fleischmann. Martin Fleischmann suggested that I volunteer for the task of reviewing the theory posters. And initially that sounded reasonable, and then I thought to myself, gosh, that's a real quick way to get yourself real unpopular. Because the way the theorists work is if you discuss somebody else's theory, if you make the mistake of not suggesting that the person should win the Nobel Prize for the theory, then offense gets taken. What's worse than that is, for those of you who know my style of preparing for presentations, I begin making my view graphs typically an hour before the presentation. And as a result, I frankly and clearly confess I haven't even seen all the posters. I hope to see them today, so my review is going to be very much less than adequate. The abstracts that are listed in the book are by generally these authors. And I think what I'm going to do is go through an incomplete list of what some of the folks have suggested. I think at the time when I'm going through it, if I've made a grievous blunder, and if the author is here and would like to correct me, perhaps it would be very appropriate. However, in backup for it, this exercise we're going to go through shortly will hopefully do a much better job on outlining the essence of what these things are about than I would have been able to do had I been completely prepared in the time given. But basically, to start through, Weber's basically coming from a not classical quantum physics, but a more traditional physics point of view, and has been looking at some of the ideas that have been suggested. A number of folks have been looking at deep Dirac states, and there's experimental evidence that supports the positron-electron version of compact states, but past that, in the case of deep states associated with electrons and nuclei, also the treatment of spin-spin interaction, there's serious questions as to what the right way to do it is. And clearly you need a relativistic description. If I've not misphrased Weber, that's part of the message. Point charge models, a lot of people have said, well, if an electron can screen the interaction between two durations, you could get estimates using point charges. In fact, Weber's suggesting we should do better. And he's additionally criticized, provided criticisms of some of the assumptions that gone into Preparato's model. Aliev's paper, at least from the abstract, points towards what I'll call a classical Russian school of thought. And the classical Russian school of thought has it that somehow the deuterons are accelerated and they fuse. And it's along the lines of fractal fusion, but it's not fractal fusion, but fractal fusion, at least in my view, gets shorted out. But these are attempts. This theory and quite a few other theories are attempts to actually provide mechanisms to accelerate deuterons on a microscopic scale. Bush discusses the electron-catalyzed fusion model, and Bass is discussing a resonance transparency model. And I'm not sure whether I should even try. Maybe I should ask Bush to explain, but at least a while back, the basic idea is that wave function going and reflecting has nodes, and if the...
This is totally different.
This is all right. Given that I actually wasn't able to make it over to your poster, I give you my apology, and you'll have a chance shortly to summarize the...
Yes, it's a totally different model, so it probably does help to read the posters before you review them.
Yeah, it's probably best not to volunteer for the job of summarizing posters, but... Okay, I will ask my friend and colleague to summarize his work shortly when we do the data extraction algorithm. The Chinese paper was looking into the possibility of weak interaction mediated reactions. Basic idea, one such as electron capture by a deuteron in order to make a weak interaction produce device or object which would participate in further reactions. I think that they're not here, which means that I'm free to babble on about this one in the absence of too much opposition. But one problem with weak interactions that I encountered when I worked on them is that the weak interaction is kind of weak. It really is very weak, and even though you can make a fair amount of progress mechanistically, at least when I plugged in the numbers, I couldn't get them to be sufficiently large to do very much for me. Williams is presenting a model where he's thinking about the neutron as being composed of a proton and electron, and the deuterium as being composed of two protons and an electron. And the idea being is that if you look at it that way, when you consider a fusion process, perhaps you can get some additional physics. On the one hand, such a proposal would face in this day and age quite a bit of criticism. On the other hand, you can actually find in Physical Review many years ago a proposal of Dirac that's not too dissimilar. However, the next paper, New Model for Wave Corpuscle, I guess I think I'm going to have to duck out on that because I didn't see the poster, I don't understand the abstract. But this author's here. I extend an invitation to help clarify this during the data extraction. The next paper, this one, basic idea is that if you have a lattice, things vibrate and you have fluctuations. If you have a large number of atoms and things are energy is distributed statistically, there's a small probability of having highly energetic systems. And this fellow has done a simulation of, I think, 400 bodies and calculated the fluctuations and demonstrated energy fluctuations on the order of half a volt. This topic was of interest early on in the discussion. There's a number of papers in literature on it. A lot of folks think that the fluctuations are not enough to describe it, but again, the issue of fluctuations is ongoing in condensed matter physics. Kozima got up and made a comment not too many minutes ago about the neutron, trapped neutron and channeling neutron issues. And basic idea is that the neutron can, it's a real neutron instead of a virtual neutron. My neutrons are negative energy, but these are positive energy neutrons. So the idea is that the neutron initiates a reaction. You have an energetic nucleus which will subsequently react. And he's proposing that you might have a neutron generation to give rise to some feedback to continue the reaction. And again, if I've screwed it up badly, please fix it. Pavlovich has discussed screening between deuterons in the abstract. And again, that's an issue that's quite a few folks are interested in. Indech, this paper looks to calculate kinetic impact fusion rates based on heating up a metal and making estimates of velocities, I presume including screening as well. And the other ones, I was running out of time and room. Page has some calculations of 2D proton conductors, which look to be relatively good, at least from the abstract, look to be relatively good chemical physics type model, condensed matter chemical physics type model. And at this point, there German fellow Chrysler, has came to me and discussed his model of new model for a proton. The standard model has a proton being made up of 3 quarks and multiple nuclei as being made of a collection of quarks. This proposal is one that has a model of the proton as a whirling object that would have different properties and would have different fusion rates. I didn't get to the others, and I think this is as much as I have, and I think I'm going to stop before I start babbling on without even having any idea what I'm talking about. So I will stop.
The plan, Tom is going to be scribe, Peter is going to be interlocutor, and I'm going to be timekeeper. Now, Tom, if you'll put that. The first question that we're going to address is, to what extent do we agree what some of the major issues in the theories are? And as a starting point, just to get us going, you'll notice that in the first column is the theory. Tom will put down the name of the author of the theory. The second column, it's been suggested that how one deals with Coulomb barrier, what mechanism, and we'll let Peter be the first example of how one deals with the Coulomb barrier issue. And then the second column is devoted to the question is how does one couple nuclear energies to chemical energies. There's a third column there, which is an invitation to those who feel that there is something else of equal or greater importance that it should be in the list. And then as we go down through the list, we will enumerate how it is in very shorthand terms, how it is that one has dealt with these issues. So Peter, if you will start off, you're the first theory, so Hagelstein compares there. How do you handle coolant?
Okay, yeah, as described, I cheat. I work with neutrals and then hope that if I can get my neutrals close, I don't have the Coulomb area. And then the energy transfer mechanism is this frequency shift business.
So neutrons, right? And how do you handle the energy coupling?
By frequency shifting a lot of phonons. Coupling is to phonons and it's through this frequency shifts of vacancy modes.
Okay. Do you have any other topics? Peter believes that those are the topics.
Could you ask people whether it's a surface or a volume effect?
That's good.
Surface or volume? Okay. Any other suggestions for categories across the top?
Oh,
Well, there can't be too many.
What's your answer to that one?
Has it been reduced to numbers?
Then, well, we'll get to that.
I think,
I mean, that's important.
I think that for now, I think that if we have too many columns, we won't finish in the 10 minutes that's allocated.
Well, I
Let's do
would
it
say
right
that's
now.
more basic. Just environment. Surface or bulk, it depends upon size.
Okay. We have two sections. Let me just clarify. The first thing we're doing here is trying to get what are considered major issues in terms of the subject matter being addressed. The second section, which we'll get to in just a moment, deals with more the characteristics of theories in terms of their ability to predict or not predict, or to predict things which have already occurred experimentally and to predict experiments which should be done in other projects. And then there's a what else column that. So let me defer the question of numbers and whatever until the second section. Yes, Tom?
Maybe whether it did with light water is applicable to light water reactions.
Actually, no, there's a place for that in the second one.
Yeah, I think that goes in the second.
Yeah.
Second characterization.
Yeah.
I'm not going to push too hard on the quantitative at this stage of the game. I think that will show up also in the second.
I think the answer will be yes all the way.
Yes.
Okay, but in terms of surface or volume, my theory at the moment is a near surface thing. It's halfway between surface and volume. I'm considering volumes in the neighborhood of, or distances in from the surface under 10 microns or thereabouts as being relevant.
Okay, for purposes of expediting this operation, I'm going to be fairly strict. What I want to do is give everyone something of the order of 30 seconds to give me a headline. Peter, go down the list of players.
Is the relation of theories to two things connected short to crystal field? First, perfectness of a crystal, or to crystal letters. If it plays any role in your theory, what is the requirement to the defect-free range? Yes. If it doesn't play, it is a peak. Yes. Second, what is the relation of your theory for the non-equilibrium condition in a crystal? Yes. Because it seems that it plays any role in cold fusion.
Right. The business of that order seems quite reasonable because that can be a yes or no thing. But further, looks like it's a little bit more difficult to address shortly here. Why don't we go through the theories presented by the oral speakers and then work on the theories presented by the posters. What's the first oral speaker? Julian.
Well, first I want to make a comment. And the comment is that the kind of coherent ground state I was talking about yesterday, they're not a whim, as most of the theories which have come, but they are a rigorous consequence of quantum electrodynamics. This state were known to Heppenlieb, to very famous and appreciated statistical mechanician, okay, that working in the Dickey model for the laser proved in one of the papers published in Annals of Physics, so you from MIT should know it, in 1973, proven that above a certain density and below a certain temperature, the Dickey Hamiltonian, which is the paradigm of lasers, as you should know very well, goes to a phase transition where there is a condensation of a large classical electromagnetic field. Now, this work has been criticized on the basis of gauge invariant, and these criticisms are totally wrong. We have published, finally, after many years, because we didn't know the problem, in 1982-83, a paper showing that, in fact, this gauge invariance criticism was totally wrong. And in fact, the Dickey Hamiltonian is a good gauge invariant Hamiltonian, even though it's an approximate Hamiltonian. So the coherent ground state are a common feature of condensed matter from the basis of quantum electrodynamics. So my question, I don't want to answer this question, I've already done it. My question is to Peter Adelson, why do you want the phonons to do what they cannot do and don't want the photons to do what they love to do? That's the problem. And if we don't understand this, the concept, beyond toys and things, with toys you don't do anything. The great science is done by concepts. This is something that is being totally lost in this Aristotelian society, Aristotelian science. And the concept is that there is a general law governing the interaction of charges and the electromagnetic field, and that's QED. And within QED, the superradiant phase transition, the way Heppenlieb called it, is a rigorous consequence. So in this state, the main actors are the transverse electromagnetic fields, the photons. And this has to be taken into account. Whoever doesn't take this into account is doing violence to the laws of nature as they've been established since Maxwell, through Heisenberg and Pauli and Fermi and the great quantum mechanicians who have given us quantum field theory in the 30s. So, okay, and then, all right, you do whatever you want.
Why do you say rigorous QED?
Excuse me?
When they say Coulomb barrier, rigorous quantum electrodynamics, that's what you're saying.
No, then, of course, you have to try and understand, to embody in the particular system, you have to embody this coherent ground state and see how they work in particular situation. Now, if you have a lattice which is a little bit bigger, this makes a big difference to the gamma amplitude, for instance, which is very sensitive because it's exponentially sensitive to distances and all that. So this is something that you have to work out. But if you have the wrong tools, the wrong intellectual tools, you will never get to anything. You will do epicycles. This is exactly, the people, the Aristotelians at Galileo's time, at Copernicus' time, they have the wrong tools, and therefore, in order to square up, they could always add epicycles. But the great dynamics came out just when people understood that there were simple laws which determine the kind of orbits, the kind of arabesques that from this planet the celestial body perform. But if you go to the right place, then the great Kepler say, oh, these are the conic section of Apollonius of Perga. Can you understand that?
Giuliano, I understand.
No, this community does not understand it. I'm sorry, because now they price. No, I'm sorry. I'm sorry.
No, I understand the point that you're making with respect to the departure that you discussed yesterday. I thought you presented it well.
But this is real. There cannot be more than one truth at one time. This is what Galileo shouts. Galileo, in one of his letters, shouts to the people who wanted to put him in jail. So there cannot be one truth, more than one truth at one time. So we better square this up, because this is the truth. Truth is not a word that we use in our liberal societies anymore. Better we talk about truths. Your truth, his truth, my truth, your truth, and so on and so forth.
At this moment, in this place, we have a variety of people with different views than yours. And all I'm trying to do at this moment is the correctness of what you say. I'm not arguing.
Well, I'm saying they haven't, if they don't use the coherent ground state, they haven't got any truth, because this is a rigorous consequence of quantum electrodynamics. So essentially, they are denying something that is already known. That's a problem, for me at least.
We understand. I understand the argument. So the question: Will you accept the statement that what one needs is, for purposes of handling that particular question, which you have raised in many forums?
Well, the Coulomb barrier is just due to this coherent plasma oscillations.
Will you accept that rigorous QED handles that as your approach?
Yes.
Okay. Can we write that down and then?
Energy coupling, of course. The phonons. The phonons are such a minor thing.
Yours.
So the photons, of course, are coupled to the
so
system.
photon coupling is the mechanism.
But photons, not single excitation, but state of high.
Where does the energy?
Classical kind of high amplitude fields, not little excitation like we have in, or little fluctuation like we have in particle physics.
We're going to rapidly run out of time.
Surface, not surface.
Okay, so it's a volume.
Not volume. Of course, the question is, let's call it mesosurface. Okay. Quantitative, yes. Of course.
Yes. Okay. Everybody's going to say quantitative. All right. Next was Lee.
Thank you. My model is resonance penetration to overcome the Coulomb barrier problem. The energy coupling, I didn't talk, but if you want to be right on something.
No, where we are is where you are today with your theory. If you haven't addressed it at the present state of your theory as presented at the conference.
That's collective inner converging of electrons. It's a volume effect. And it's quantitative because I have a formula tau equal to ma squared theta over h. And for light water,
we're not doing that.
Okay.
Now let's see.
So it's the volume?
Yes, volume. Yes.
Kim. What's that? Volume?
Volume.
Okay.
Is Kim here?
Kim?
Yeah. Who's this next?
Young Kim.
Oh, Young.
My answer is yes.
But what does it mean?
Yes is having. No.
Yes doesn't mean anything.
No.
Okay. Young, you're keeping your Coulomb barriers, right?
Yeah.
So
it's a speculation, but I have. I'll say.
No, yes is not.
And the coupling is kinetic. But yeah, you're just having your positive Q values smash into things. So it's a.
My theory is not revealed that yet. Surface, volume, both.
So it's both in the case of surface. On the Coulomb barrier, it retains the Coulomb barrier and does penetration, basically modifying the gamma structure.
Coulomb barrier can be cancelled into parameters.
And what about energy coupling?
It's kinetic. Well, no, he does address it. He's not got an anomalous mechanism.
Coulomb barrier can be cancelled only by a counter physical effect. How can you cancel it then? So if you have a barrier, you have to take the barrier down. That's the only way to cancel the barrier.
All right, Kevin. Energy minimization in periodic balance.
Well, the energy barrier, you're talking about correlation effect.
Well, we're talking about what correlation effects are. It's energy minimization is the whole thing. Energy minimization.
Well, energy minimization is always there. That's a condition for stability in quantum mechanics.
That's how you do correlation effects.
Yeah, can you write
but
that
you have to know
correlation
what the
effect?
energy is.
That's the basis
You
of
don't.
Paul's calculation, is a correlation.
The basis
no way
of
of
Paul's
knowing.
calculation is energy minimization in periodic bound systems.
But
Bound
you,
is important.
yeah, but you cannot minimize what you don't know.
We do know.
Of course you don't, because you have to have an ab initio calculation, which you don't have.
We do it in
Can I not interject?
But of course you don't.
All I'm interested in.
You don't have an ab initio calculation.
You write down how you characterize your vessel.
I just fudged up. Come on. I mean, it looks like we are in a carpet.
How do you do energy coupling?
That's the soup of this.
Cooperative, many-body, phonon coupling.
On energy coupling?
Phonons.
But you know that the energy of a phonon is so slight. You can't do anything.
Phonons, okay. Surface and volume is quantitative, yes.
Okay. Who's next? Now we go to closers.
Bush got slighted, so.
We'll start with Mike first.
Sure.
The Coulomb barrier would be gotten through by electrons in deep orbits catalyzing higher fusion rates. Energy coupling, I don't think a lot of that in the model, but I would definitely vote for phonons.
If you'd like to.
Definitely be a volume effect. There could be some sort of, let's say, volume. Predictions, I can't imagine you could have a successful model that didn't have some prediction. Why don't you put mini and then translate that into this by saying yes, 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 yes.
I'm not sure quantitative is, everybody who's a theoretician who doesn't do quantitative is, I don't think they call themselves theoreticians.
Reducing the numbers is different.
Okay. In terms of the next one, are there poster authors who'd like to volunteer to join the list?